Okay, so good morning. I think it's time to start. So as you saw in the last class, we finished classical cryptography, most of the basic stuff, and which was very old stuff. Then in the private key cryptography, the symmetric cryptography, we are going to mainly focus on two popular schemes. One is DES, and another one is AES, Advanced Encryption Standard. And both of these schemes I am going to describe. But before that, they are based on one key strategy, the similar idea of substitution and permutation network. So, both of these are known as block ciphers, and these block ciphers basically are based on substitution and permutation network. So, we take binary bits and then do all these in different kind of, mappings are used in between. So I'm going to describe. So I think we started that thing in the last class. I'll go over it again with an example. I will show you how substitution and permutation network works. And then, later on, we will talk about it, how with bunch of modifications in that scheme, we can come up with AES and DES, And there are interesting stories like, how do you break? First of all, how do we break? So in fact, I will tell you some idea about substitution and permutation network. There are two popular schemes through which you can actually, do the cryptanalysis. One is linear cryptanalysis, another one is differential cryptanalysis. Both of them are bit beautiful, right? So basically it involves, so I need you to pay a little bit more attention here. How do we analyze? Normally people skip in the first lecture. In the first time when you teach these things, people try to skip these things. And when you are a little bit more expert, you can come back, but no problem. We are going to do it because what we have done, what I'm going to do is I'll take a small example and try to analyze that, because, if you want to look into whole totality, it is going to be a tedious job at the first time, when you are reading this. So we are going to talk about it. So first of all, today I'm going to talk about, I will again recall the substitution permutation network. Then I'll take an example of it. Then I'm going to do the linear cryptanalysis of that. Okay, and I'm going to use certain tricks like piling up lemma. So basically, whenever you want to prepare a food, you require some ingredients, right? So first I'll cover a couple of ingredients. Most of these ingredients are probabilistic in nature. So you need to be really good in probabilities so that you can understand these things. And then we look at the piling up lemma, and then using piling up lemma, we will analyze again the same example which I'm going to describe today. How do we arrive at an attack? Okay, those kind of things we are going to do. And I think probably, I hope I will be able to finish linear cryptanalysis today. No, not, I'll prepare all the ingredients today. Tomorrow I'm going to do the linear cryptanalysis by using linear approximation to S boxes. That technique I'm going to talk about tomorrow. And then we can do the differential cryptanalysis, okay? So let me start this substitution permutation network again. So just have a patience, observe it. You don't have to write everything, because everything is there on the YouTube lecture, right? You can always watch if you want. And all the slides are also available for you to look at it. Okay. So normally in this block cipher, we use sequence of permutations and substitution operations. Okay. And it's kind of a iterated cipher. There are a bunch of round functions, and each round there is a key schedule, right? So this key schedule, so from a random key, we generate a key schedule. I'm going to show you one way of generating the key schedule. There are many ways, and depending on how complex you use the technique, you can think about it in a much better way. You can come up with a system. So encryption of a plain text will be through n similar rounds, and we use a random binary key, okay, of some specified length. If length is small, you can break the system easily. So if the key is of longer size, you can make sure that we are not able to break it. And Using this random key, we construct n round keys, or we also call them sub keys, k1, k2, kn, which are used in each round. So normally, so starting with a plain text, so basically a bunch of binary strings, you do some calculate, substitution permutation, and then you add one key, k1, and then go again do substitution permutation, add another key, k2, and do substitution permutation again, add another key, k3. Like that, we keep on doing things, right? That is a basic idea about this. Each round, we have a round key. Okay. So, so basically, that means you can see that initially starting with a plain string of plain text. So in between, you will be getting some state of the bits, right? Bits will be in some state, right? So, so round function takes the two inputs, one, the round key, and the current state of the bits. Current state of the bits and a round key, and then you kind of XOR it, right? That is something you can do it. So next state is something like this. So this is a, we can write it like WR. The next state, rth state, is function of r minus 1th state and the round key k, right? So normally we take XOR, but you can, there are different ways you can do it. But, so this is something, a general strategy. So WR minus 1 means at the round R minus 1, we have a state of bits. Okay. So plain text have changed to some states, right? Some bits are there. And initial state is there, which is the plain text, X, right? W0 is the plain text. So ciphertext Y is a state after all n rounds. Okay. So round 1, we have the plain text. So round 0, I will say. Round 1, we have, function of W0 and then key 1, K1, schedule key, W2, K2 schedule key with the state W1, and so on, so forth. Finally, after round n, we get a state which is a ciphertext. Okay. Again, bunch of bits. Starting with a plain text of some size, a binary string, and finally we are getting a binary string. Okay. So this is the thing. So round function and key. Now, so the idea is, how do we generate these round keys? So round keys are generated through some random key, and there are many algorithms. I'm going to give you one example, which is very simple one. Okay, there are different ways you can generate the schedule keys from key. You will see that actually in our DES or AES, there are more complicated algorithms are there to generate the schedule keys. Okay, so that is a key thing. Okay, and of course, if we should be able to do the, so that this function should be invertible, right? If we can do inverse, then only we can decrypt, right? So this is important, that the G should be injective function. Okay, if second argument is fixed, so in that case, we have all these things from the ciphertext. You apply the inverse on the state and the key, you get one less state and so on. Finally, you can get the plain text X, right? So it should be reversible at each step, right? Of course, you are not going to do these things by hand. You have to write a good computer program. So people who are good at competitive programming can do some of these things, right, easily. Okay. Anyway, so now I'm going to describe. So that was a general strategy. How do we work this simple iterated cipher? Substitution permutation network, SPN. So there are two positive integers, L and M. Plain text is a binary vector of length L into M. So binary vectors of size L into M. Okay, L and M are two positive integers. So LM is known as block length of the cipher. Block length of the cipher. So plain, okay, that is plain text. Ciphertext is also finally a string or a bunch of bits of size LM. Okay. So plain text is a bits. So plain text is a binary string of length LM. Ciphertext is a binary string of length LM. Fine. And there are two components. So pi s and pi p. So pi s is nothing but known as S box or substitution box. We call it as S box simply, right? I will show you later on how do we attack, mount an attack by getting a linearization of substitution box. Okay, and the permutation. So in in general, what we do here, I'm going to describe now. So pi s is a permutation of the 2 raised power L, those many bit strings of length L, right? So 0, 1 raised power L, there will be 2 raised power L strings, right? So basically, it's a permutation of the 2 raised power L bit strings of length L, and pi p is a permutation of the integers from 1 to Lm, right? So pi s is used to replace L bits with a different set of L bits. Take L bits and replace it with a different set of L bits. That function is done by pi s, and pi p is used to permute Lm bits by changing their orders. Okay. Understand the difference between pi s and pi p. Pi s is changing L bits with a different set of L bits, and whereas pi p is used to permute the Lm bits. I mean, their order is changed. Basically, some permutation is applied, right? Got it? So these are the, why it is called substitution, because you are taking L bits and substituting with some other L bits, right? So that's why it is known as substitution. Obviously, this is also kind of permutation, but we specify substitution because we are taking L bits and replacing it with some other L bits, right? And this is your changing the order, right? So this is a permutation. So I think you can, because mathematicians like, so idea is really very simple, but you want to formalize it mathematically, so you can denote some notations. X is equal to x1, x2, Lm is a, the plain text. You can divide into these blocks, L bits, L bits, L bits, right? Like something like this. So SPN will have n rounds in each round, except last round. We will perform m substitution using pi s, followed by a permutation using pi p. So prior to each substitution operation, we will incorporate round key bits via a exclusive OR. Okay, this is a very specific thing. Now we are generating. So we are actually, that function is simply addition. Okay, exclusive OR from the plain text, right? That's what we are going to do. So here is our crypto system. Formally, we have Lm n is positive integers, pi s is the permutation, or substitution basically, pi p is the permutation. Then we have plain text and ciphertext are bit strings of length Lm, and then there is a key. Okay, so all possible key schedules that can be obtained from the initial key using a scheduling algorithm. So from that key, which is very random, random key. From a random key, you can generate a key schedule for each round. Okay. So now, formally, the algorithm is written in a pseudo code like this. So UR is the input to S box in round R. VR is the output of S box in round R. WR is obtained from VR by applying pi p, and then UR plus 1 is the coming from DUR, WR basically. So this is the algorithm you see. And so first and last operation in SPM are exclusive OR with subkeys. Okay, so this process is known as whitening. Okay, so I think we talked up till this place. Now here is an example. If we take LMN as 4, and so we remember this example, we are going to mount an attack on this example only to illustrate the whole process. Now, I think I am writing data in terms of hexadecimal notation. I hope you understand what is hexadecimal notation. So 0 to 9, we have bits, and then A to F, right? We again have bits. So all the 16, of length 4, there are 16 vectors, right? You can map them, and basically you get this hexadecimal notation. So now basically, the first function which we are going to use substitution is, so 0 to F substitution is something like this. Okay, and so you see now substitution means it is replacing 4 bits, right? Each one is a 4-bit vector, right? L bit substitution, the first part, and second part is permutation. So all this you are changing the order like this. Okay, 1 to 16, some permutation I am using. You are free to use any other permutation, right? Got it? Now, so what is left? We need to take a random key, and we should know how to generate the key schedule. Different keys, K1, K2, Kn for each round, right? Now, here is a typical scenario here. So all these, so X is a plain text. I think it is not visible at the top, but it's okay. Then there is a K1, the first key in the schedule. Then these are the S boxes, substitution S1, 1, S2, 1, S3, 1, S4, 1. Then again, permutation. First substitution, then permutation of bits, then substitution of L bits, then permutation like that, and the XORing with different key schedules. Finally, you will get the Y, right? This is the typical scenario that will happen. So there are 16 S boxes used. You can see that, right? Because I runs from 1 to 4 and R runs from 1 to 4. There are 16 X boxes which are used here. Now, this is actually, why it became very popular, because it is very easy to implement actually, in terms of complexity also. Memory requirement is very less, L into 2 is for L bits, and you can implement it just by lookup table, okay? So implementation is very easy for this substitution permutation network, okay? Now, we need to find out a way to generate these from a random key, right? How do we generate the key schedules? So if you take 32 bits, if K is a 32 bits vector, how do we get different subkeys? Okay, so let me show you one way of doing this. This is a random key K. So round key is how we can get the first round key. Take the so these are L is equal to 4, right? So 4 bits, 4 bits, 4 bits, 4 bits. First 4 vectors I am putting as K1. Right, so 0011, 1010, 1001, and 0100 is the first subkey. Second subkey is shift. Starting from 1010, next is 1001, 0100, 1101. That is the next one. Simple, There could be more complicated ways. I'm just saying that from 32 bits, I'm just doing this shifting and then I'm generating these key schedules. Right? More complicated key scheduling algorithm will be more difficult to break actually, so this is just a simple thing. And then finally, now, so basically suppose this is a plain text, right? And remember, as I mentioned, this substitution permutation network is not secure for small keys. So essentially, how do you generate large keys? That is the crux of the problem, right? If you can generate large keys, you can safely say that, yeah, system is secure, okay? So here is a working example with the plain text. Use that K1 and do all these substitution permutation, XORing with key. Finally, you get the ciphertext, right? Starting from plain text. So any question? All this was very easy, right? Real beauty will come now. So this is very easy, right? No question here. So now you will see that. Just think loudly. How do we break this system? Any approach? So you saw the example, right? So जहां ना पहुंचे रवि वहां पहुंचे कवि, right? Probability business. So probability business is very, very important. You will see that just by observing, certain probabilities, you can actually think about it. Of course, I will make some assumptions here to simplify the analysis. I'm telling you, this is a very detailed analysis. Normally, people don't teach these things initially, but you should get some flavor of beauty, right? So that you can be a good cryptographer later on. Anyway, so I am going to talk about it. So attack on this substitution permutation network, okay? And the first, as I mentioned, there are two kinds of attacks that are possible. One is linear cryptanalysis, another one is differential cryptanalysis. Both were very popular. The first time when DES was broken, using some of these techniques, it is very, very, beautiful paper. You can find those papers in the literature, right? And if you want to read it, they are thick documents. But anyway, so we are simplifying all these things. I'm going to focus only on this small example and trying to show you how we can break the crypto system, right? But then there are certain assumptions. So now you have to pay a little bit more attention. So first I'm going to talk about the strategy. What is the strategy, right? And this strategy assumes certain things. Suppose it is possible to find a probabilistic linear relationship between a subset of plain text bits and a subset of state bits, those WRs, right? Suppose it is possible to find a probabilistic linear relationship between a subset of plain text bits and a subset of state bits. Okay? Some probabilistic relationship is there, linear. In other words, there exists a subset of bits where exclusive OR, because we are doing exclusive OR everywhere, right? Where exclusive OR, the summation exclusive OR behaves in a non-random fashion. Okay? It turns out that, on the value 0, say, with probability bounded away from half. Okay? This is the kind of assumption that we are taking, right? Okay? This is the, so, there exists a subset of bits where the exclusive OR behaves in a non-random fashion. Okay? Means there is some linearity, right? So, now assume that an attacker has a large number of plain text and ciphertext pairs. So it's a plain text attacks. We have a large number. So normally, when I show you how to break this system, we have assumed that there are about 800 pairs, 800 such pairs of plain text and ciphertext. Plain text and ciphertext, right? And that is available to us. So now assume the attacker has a large number of plain text and ciphertext pairs. So all encrypted with same unknown key. Okay. Somehow you are able to do this. Okay. So this is known as known plain text attacks. For each of the pair, we will begin to decrypt the ciphertext using all possible candidate keys. Okay, using all possible candidate keys for the last round of the cipher. This is the thing what we are trying to do. For each of the pair, we will begin to decrypt the ciphertext. So plain text and ciphertext, there are 800 pairs available to us. What we are going to do for each of the pair, we will begin to decrypt the ciphertext using all possible candidate keys for the last round of the cipher. Because that length is fixed, so you know that so how many possible keys are there? You can just try one by one, right? One, another one, right? So all possible candidate keys for the last round of the cipher. For each candidate key, we compute the values of the relevant state bits involved in the linear relationship. There was a linear relationship we assumed, right? So we are basically, for each candidate key, we compute the values of the relevant state bits involved in the linear relationship and determine if the relationship holds. Okay? Just pay attention here. If the relationship holds, sometime it will hold, sometime it will not hold, right? If the relationship holds, when it does, an increment, we increment a counter, okay, corresponding to the particular candidate key. So at the end of the process, we hope that the candidate key that has frequency count further away from half, okay. So this the number of plain text cipher text pairs, gives you the correct value for the key bits. So based on this analysis and assumption, we will say that because there is a linear relationship, we will be able to get the correct key. Okay, if you observe this. Okay, so now I think again, do you understand? Do you understand what is going to happen here now? Again, I am telling you, strategy was, suppose it is possible to find a probabilistic linear relationship between a subset of plain text and a subset of state bits. Okay. In other words, we are saying that there exists a subset of bits whose exclusive OR behaves in a non-random fashion. It takes on the value 0, say with probability bounded away from half. Okay. This is the kind of relationship we are looking at. Then we assume that attacker has a large number of plain text and ciphertext pairs. Okay. then we are just screening all the possible candidate keys and see if there is a relationship, you know. Okay, so basically, so we are looking at this counter, okay, and at the end of each process, we hope that the candidate key that has a frequency count further away from half, you know, this is the, then, you know, this will give you the number of plain text and ciphertext pair, okay, which gives you the correct value of the key. So basically, let us now look at the piling lemma. So I think this is also another machinery. So I gave you the general strategy. Now the piling lemma, okay, let x1 bar, x2 bar, and so on are independent random variables taking the values from 0 and 1. Okay. So now basically again you see that we have the binary strings of the plain text, binary strings of the ciphertext. So basically for each bit we are actually, so suppose x1, x2 are the independent random variables, and suppose p1, p2, you know, p3, p4 are real numbers between 0 and 1. Suppose that probability that xi bar is equal to 0 is pi, okay, and xi bar is equal to 1 is 1 minus pi, okay. And we also have that, you know, when I and j are disjoint, I mean they are not equal, you know, you know, we have the independence of xi bar and xj bar, you know. This is an important fact. Now then I can compute these probabilities. Probability that xi is equal to 0 and xj is equal to 0 is how much? Because probability that xi is equal to 0 is pi, and probability that xj is equal to 0 is pj. When we take it combined, it is basically product of pi and pj. Probability of xi is equal to 0 and xj is equal to 1. So probability that xi is equal to 0 is pi, and probability that xj is equal to 1 is 1 minus pj. So the combined thing is the product pi 1 minus pj. Probability that xi bar is equal to 1 and xj bar is equal to 0 is 1 minus pi times pj. In a similar manner, when both are 1, it is product of 1 minus pi into 1 minus pj, right? From the previous slide here, so from these things, the probability of xi is equal to 0 is pi, and probability of xi is equal to 1 minus pi, and under this assumption, we will be able to compute these probabilities easily, right? So when we are able to compute these probabilities, now I can compute this probability of this sum, xi plus xj is equal to 0. Now xi plus xj could be 0 when both are 0, or both are 1, right? When both are 0, when this is 0, this is 0, the probability will be pi times pj, right? And when both are 1, the probability will be 1 minus pi times 1 minus pj. So overall probability will be the sum of these two, okay? Okay, so this is the probability of xi plus xj is equal to 0. Similarly, the probability of xi plus xj is equal to 1 is, you know, so now this could be 1 when this is 0 1 or 1 0, right? When one of them is 0 or another one is 1, right? So there are two possibilities. So in each case, so we have the probability pi times 1 minus pj plus 1 minus pi times pj, okay? Simple probabilistic calculations which you can do. So there is a lot of, you know, it's really very nice. This attack thing is very beautiful. I mean, undio, right? A lot of ingredients are there, right? So you need to prepare a lot of preparation. So this is one such preparation, right? So oh, sorry. Okay, now I'm going to look at what is known as bias of xi, our random variable xi bar, biasness, you know. So it is defined as epsilon I is equal to pi minus half. Okay. And clearly, since pi is the probability between 0 and 1. So this whole thing lies between minus half and half. Now probability of xi is equal to 0 will be half plus this biases, epsilon I, right? Because of pi minus half is that epsilon I, right? That's the bias. So, and this can be written as half minus epsilon I, right? From that formula. Now we are ready to give you the piling up lemma. So we are computing epsilon I1, I2, I3 dot 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 Ik. Okay. So we are looking at this variable. I mean, we have given you everything I have given you for two bits, right? Now we are looking at there are n, there are k bits, right? Xi bar, Xi, Xi1, Xi2, and so on. I think one is missing here actually. No problem. So and so on up to Xik bar, right? Exclusive OR of these k things, right? So what is the biases of this random variable? Okay, that we can compute. So then the result says that piling up lemma says that this value is 2 raised power k minus 1 times partial product j is equal to 1 to k epsilon ij. And many times when the things are complicated, proofs are very simple using induction, right? We say that we can prove it by induction. How do we prove it by induction? So k is equal to 1. Obviously, it is true for k is equal to 1 because we just obtained that result, right? Now we compute for k is equal to 2. So k is equal to 2, we have these two things, right? xi1 plus xi2. Now this is 0, then I can compute what is for this. I mean, just like the previous thing, right? So now this could be 0 when this is 0, or this is 1, this is 1, right? So basically we can compute the probability values because these things we have obtained from the previous expression, right? So half plus epsilon I1 times half plus epsilon I2 and so on up to this expression, right? We can simplify this. This turns out to be half plus 2 times epsilon I1 epsilon I2. So that means we have epsilon I1 I2, which is what we want to compute for k is equal to 2, is basically half plus 2 times this minus half, right? Because that's how pi minus half, that is how it is defined, right? So this simplifies to 2 times epsilon I1 epsilon I2. So we have got the result for k is equal to 2. So result is true for k is equal to 1, result is true for k is equal to 2. Assume that the result is true for k is equal to L, and then prove that the result is true for k is equal to L plus 1. That is how you do the induction, right? So now assume that it holds for k is equal to L. Now L is of course at least 2. We want to prove that it is true for k is equal to L plus 1. Now we consider xi1 zor up to xi L plus 1. I am taking one more extra bit, right? This can be written as those L bits plus the last bit, right, which we added. Now, here by induction hypothesis, result is true. So I will assume that expression is like this from the induction hypothesis. And for the last bit, we know I can compute it as epsilon I plus 1, right? So biases of, we can compute all L plus 1 bits will be 2 times this expression times epsilon I1, I2, right? And so we simplify, we get the result what we wanted. So all the preparations are ready, but I will not give you Undio today, tomorrow, because it involves a lot more things, right? So slowly, first try to understand the ingredients, then we'll go to the main thing. If you do it everything today, it's all right. Slowly eat. Otherwise, there will be a problem, right? So tomorrow, 11 o'clock, we will meet and we will see this analysis on this specific example. I'm not going to do into the general thing, okay?